Hi. So we are doing the chapter number 6, I guess. So the name is Isomorphisms. We have done isomorphisms, everything, their theorems, their properties. Now we are going to talk about a special kind of an isomorphism, which is known as an automorphism. So let's write the topic, which is automorphisms. What are the automorphisms? Automorphisms are the isomorphisms from the same object to the same object, or you can say from the same group to to itself, from a group to itself. Okay, so the definition would be an isomorphism from a group G to itself is called an automorphism of G. Now remember, we have given an example 6, which is this one. This one. So this example, which is from G to itself, given by a matrix M, and we have a map phi M of A is M A M inverse, is an automorphism. It's is an automorphism map, okay? Because phi M is generates defines an automorph is an also isomorphism, but like the map is from the same group to itself, so that's why it becomes an automorphism. Okay, but once we go in and then learn about a more special kind of an isomorphism, then we will give it a new name to phi m. Okay, so let's define an example. Example 11, which says that the map, or you can say the function phi from C to C. Let's say you have from C to C given by phi of a plus b iota, where C is a complex number, given by phi of a plus b iota is equal to a minus b iota. Like it just conjugates the complex number, is an automorphism of the group of complex numbers under addition. Similarly, if we just restrict the complex numbers to C star, so you can say the restriction of phi from C star, which is C minus 0 to C star is also an automorphism of the group of non-zero complex numbers under multiplication. Okay, perfect. So what do you need to check whether a map is an automorphism or not? You just need to check that it is an isomorphism. Okay, and the property that it's a map from the group to itself makes an automorphism. Right. Perfect. We can give another example. Another example is about that late R square is defined as ordered pairs. It contains ordered pairs where A and B are real numbers. Then you can just say there is a map phi from R square to R square given by that phi of A comma B is nothing but B A is an automorphism of the group R square under component-wise addition. Okay. Now, what is this geometrically? Geometrically, it's just a reflection of each point across the plane. And it is given by the line y is equals to x. And more generally, any reflection across a line passing through the origin or any rotation of the plane about the origin is an automorphism of R square. So you can say generally any reflection like phi across a line passing through the origin through the origin or any rotation of the plane about the origin is an automorphism of R square. Now, the isomorphism we have presented in example number 6 between from SLR2, SL2R to SL2R have also a different name, and that name is given by a new definition which we present now. The definition is about Inner automorphism induced by A. There we have induced the automorphism by M. Here we will now induce the automorphism, define it in inner automorphism by some element of the group. So let's say G be a group, and let A and G be an element. The function phi A defined by phi A of x is equal to AX A inverse for all x in G is called the inner automorphism of G induced by A. Induced by some element A. Perfect. Now you can simply say that inner automorphism is also an automorphism because it's also a map which is isomorphism, and it's also a map from G onto itself, and it's just definition is given by this phi A of x. Okay, so any automorphism given by this definition or of this kind is known as an inner automorphism. Perfect. Now let's see an example of this kind. So there is an example which we have done in the very start of the course, defined by D4, and we now present an inner automorphism of D4 induced by R90. So the action of the inner automorphism of D4 induced by the element R90 is given in the following table. Given in the following table. Let's define the table now. So we say that we have element x, we have a map which is phi R90, and we now do R90 x R90 inverse. Okay. Now what's going to happen to the elements of D4? How many elements are D4? There are 4 elements of D4. So this is going to happen to the elements of D4. So R0 under this map will go to R90, R0, R90 inverse, and that is again same because it's just identity. Then we have R90 itself. So R90 R90 and R90 inverse is going to be same again. Is R90 and R90 inverse will cancel out each other, gives us identity, and then just multiply and nothing happens. Perfect. Then we have R180. R180 R180 will be transformed and remains the same. Similarly, R270. So R270, sorry, it should be 90, 270, 90 inverse will remain same also. Then comes the twist. So we have this element H there, which is horizontal reflection. That is going to be changed into the vertical reflection. Then we have vertical reflection that is going to be changed into the horizontal reflection. Then we have D, which is the diagonal one. That is going to be changed in the other diagonal one. Then we have D prime goes to R90 D prime or 90 inverse to the D. So this is how the map is going to map by phi R90 going to change the elements of D4. Okay. And it's surely an inner automorphism. Right. Perfect. Now we know that when G is a group, we use notations, you can say. Let's write notations. When G is a group, we use aught G to denote the state of all automorphisms of G onto G. Okay. And we use I double n of G to denote the set of all inner automorphisms of G. Perfect. Now we have defined all these. Here we will end this part of the video.